Welcome to this complete guide on PyTorch TransformerEncoder. In this tutorial, we're going to dive deep into understanding the TransformerEncoder architecture and all of its components. We'll start with the basics and gradually build up to more complex examples. By the end of this lesson, you'll be comfortable working with transformer encoders, understand all the parameters and their effects, and be able to build practical applications. We'll also learn how to visualize attention patterns and understand layer behaviors. Let me show you the overall architecture of a transformer encoder. This diagram illustrates how the encoder stacks multiple transformer layers, with each layer containing self-attention and feed-forward components. Notice how the data flows through the network, starting from the input embeddings, passing through multiple encoder layers, and producing contextualized representations. Now let's look at what's happening inside each transformer encoder layer. This diagram shows the internal structure, including the multi-head self-attention mechanism, the add and norm layers, and the feed-forward network. Each component plays a crucial role in transforming the input representations. Let's start by importing all the necessary libraries we'll need for this tutorial. We're importing PyTorch for our deep learning framework, NumPy for numerical operations, and Matplotlib and Seaborn for creating beautiful visualizations. I'm also setting up our plotting style and random seeds to ensure our results are reproducible. Now we'll look at the simplest possible example of creating a transformer encoder. Here's our first transformer encoder example. We're creating an encoder with an embedding dimension of 512, 8 attention heads, and 6 encoder layers. First, we create a single encoder layer with the specified dimensions and number of heads. Then we stack multiple copies of this layer to create our full transformer encoder. Notice how the input has shape sequence length by batch size by embedding dimension. After passing through the encoder, the output maintains the same shape, which is exactly what we expect. Perfect. As we can see, the input shape is 10 by 2 by 512, representing 10 sequence positions, 2 samples in our batch, and 512 dimensional embeddings. The output maintains this exact same shape, which confirms that the transformer encoder preserves the input dimensions while transforming the representations internally. Let me show you a comprehensive table documenting all the parameters of transformer encoder. Understanding these parameters is crucial for building effective models. The encoder layer parameter defines the architecture of each layer, num layers determines the depth of your network, norm adds optional final normalization for stability, enable nested tensor optimizes performance with padded sequences, and mask check ensures your masks are correctly formatted. Now let's explore each parameter in detail, starting with how the number of layers affects our model. I'm testing different layer counts to see how model depth affects the output. We're creating encoders with 1, 3, 6, and 12 layers, and examining how the output norm changes. Notice that even as we increase the number of layers, the output maintains stable norms thanks to the layer normalization within each encoder layer. This stability is crucial for training deep networks. Excellent. We can see that regardless of whether we use 1 layer or 12 layers, the output norm remains remarkably stable around 143. This demonstrates the effectiveness of layer normalization in preventing gradient explosion or vanishing as we stack more layers. Let's visualize how the output distribution changes with different numbers of layers. This will help us understand how depth affects the learned representations. Looking at these histograms, we can observe that the output distributions remain relatively similar across different layer depths. All distributions are centered around 0 with similar spreads. This consistency is a result of the normalization mechanisms built into the transformer encoder, which help maintain stable activations throughout the network depth. Now let's examine the effect of adding final normalization to our encoder. We'll compare 2 encoders, one without any final normalization and one with layer norm applied at the output. This final normalization can help stabilize the output representations, especially in deeper networks. Interesting, both versions maintain a mean very close to 0 and similar standard deviations around 1. The version with normalization shows slightly more consistent statistics, which can be beneficial when using these representations for downstream tasks. Let's explore the Enable Nested Tensor parameter, which provides performance optimizations when working with padded sequences. We're creating two encoders, one with nested tensor support enabled and using batch-first format, and another with it disabled. This optimization is particularly useful when processing batches with variable length sequences. We can see that nested tensor is enabled for our first encoder and disabled for the second. The nested tensor optimization allows PyTorch to handle padded sequences more efficiently by avoiding unnecessary computations on padding tokens. Now we'll dive into working with masks, which are essential for controlling attention patterns in the transformer. Let's create a causal mask for autoregressive sequence generation. This type of mask prevents positions from attending to future positions, which is crucial for tasks like language modeling. We're using PyTorch's built-in function to generate a square subsequent mask, which creates an upper triangular matrix. Notice how each position can only attend to itself and previous positions, with negative infinity values blocking attention to future tokens. Perfect. Looking at the causal mask, we can see the triangular pattern clearly. The first position can only attend to itself, the second can attend to positions 1 and 2, and so on. This ensures that when generating sequences, each position only has access to information from previous positions, maintaining the autoregressive property. Now let's work with padding masks for handling variable length sequences in a batch. This is extremely common in real-world applications where not all sequences have the same length. We'll create a batch with sequences of different actual lengths, 8, 6, 10, and 5 tokens, all padded to a maximum length of 10. The padding mask tells the model which positions contain real data versus padding. Excellent. The padding mask correctly identifies which positions are padding for each sequence in our batch. The first sequence has 2 padding positions at the end, the second has 4, the third has none since it's the full length, and the fourth has 5 padding positions. This mask ensures the model ignores these padding tokens during attention computation. Let's move on to visualizing attention patterns, which helps us understand what the model is learning. I'm creating a custom transformer encoder that can capture attention weights for visualization. We're generating input data with a specific pattern, a diagonal pattern where each position has a distinct feature activated. This helps us see how the attention mechanism processes structured input. Now let's create visualizations of attention patterns. While we're simulating the patterns here for demonstration, in a real implementation, you would extract these from the actual model. The heat map shows how each query position attends to different key positions, and the line plot shows attention distributions for specific positions in the sequence. The attention heat map reveals interesting patterns in how different positions attend to each other. We can see that some positions focus strongly on specific keys, while others have more distributed attention. The line plots show that early positions, middle positions, and late positions each have distinct attention patterns, which helps the model capture different types of dependencies in the sequence. Now, let's look at a practical example of processing text sequences with our transformer encoder. Here's a complete text processing model using TransformerEncoder. We're building a model that takes token indices as input, embeds them into a high-dimensional space, adds positional encodings to give the model information about position in the sequence, and then processes everything through the transformer encoder. The model includes an embedding layer for vocabulary of 10,000 tokens, positional encoding to inject position information, and a 6-layer transformer encoder with layer normalization. This architecture forms the backbone of many modern NLP models. Great! Our text transformer encoder is working perfectly. It takes sequences of 30 tokens from a batch of 4 samples and outputs contextualized representations of dimension 512. The model has about 24 million parameters, which is typical for a medium-sized transformer model. This architecture could be used for various NLP tasks like classification, sequence labeling, or as an encoder in a sequence-to-sequence model. Let's perform an advanced layer, wise analysis, to understand how representations change as they flow through the encoder layers. I'm creating a custom encoder that gives us access to intermediate layer outputs. This allows us to analyze how the representations evolve through the network. We'll track statistics like mean, standard deviation, and norm at each layer to understand the transformation process. Fascinating! We can see how the representations stabilize quickly after the first layer. The input starts with a slight negative mean and higher standard deviation, but by layer 1, the mean centers at 0 and the standard deviation stabilizes at exactly 1. This pattern continues through all subsequent layers, showing that the layer normalization is doing its job perfectly, maintaining stable statistics throughout the network depth. Let's visualize these layer-wise changes to better understand the evolution of representations through the network. These plots beautifully illustrate the stabilization effect of layer normalization. The mean quickly converges to 0 after the first layer, the standard deviation stabilizes at 1, and the L2 norm shows a slight decrease initially before stabilizing. This consistent behavior across layers is what allows us to train very deep transformer models successfully. Now let's compare different transformer encoder configurations to understand the trade-offs between model size and capacity. I'm comparing 3 different configurations: a small model with 256 dimensions and 3 layers, a base model with 512 dimensions and 6 layers, and a large model with 1024 dimensions and 12 layers. Let's see how the parameter count scales and how it affects the output stability. The results show dramatic differences in model size. The small configuration has about 4 million parameters, the base has 19 million, and the large model has over 100 million parameters. Despite these size differences, all 3 maintain perfectly normalized outputs with standard deviation of 1, demonstrating that proper normalization allows us to scale transformers to very large sizes while maintaining training stability. Let's create a visual comparison of these different model configurations to better understand the trade-offs. The bar charts clearly show the exponential growth in parameters as we scale up the model. The small model at 3.9 million parameters is suitable for resource-constrained environments. The base model at 18.9 million represents a good balance for many applications, and the large model at 100.8 million parameters provides maximum capacity for complex tasks. Remarkably, all 3 maintain identical output stability, which is crucial for successful training. Now let's explore common pitfalls when using TransformerEncoder and how to avoid them. Here's a common mistake: using incorrect mask dimensions. When we try to use a 5x5 mask with a sequence length of 10, PyTorch correctly catches this error and tells us the mask should be 10x10. After fixing the dimensions to match the sequence length, everything works perfectly. Always remember that attention masks must match the sequence dimensions. Good, the error message clearly indicates the problem. The mask shape doesn't match the sequence length. Once we correct the mask to be 10x10, matching our sequence length, the encoder processes the input successfully. Another common pitfall is forgetting to properly handle variable length sequences. I'm creating a helper function that generates proper padding masks based on actual sequence lengths. This ensures that padding tokens don't contribute to the model's computations, which is essential for correct results when working with batched sequences of different lengths. Perfect. Our padding mask correctly identifies 5 padding positions for the first sequence, 8 for the second, none for the third, which is full length, and 12 for the fourth. This proper masking ensures that the model only processes actual content and ignores padding, which is crucial for accurate results. Let me summarize the best practices for using TransformerEncoder effectively. First, be careful with layer initialization, since all layers share parameters by default. Always add final layer norm for stability in deep networks. Verify that your mask dimensions match the sequence length. Use source key padding mask for variable length sequences. Enable nested tensor with batch first for better performance. And monitor gradient norms in deep encoders to detect any training issues. Common use cases include sequence classification, where you pool the encoder output, feature extraction using intermediate layers, and sequence-to-sequence models when combined with a decoder. Finally, let's build a complete transformer classifier that brings together everything we've learned. This model includes embedding layers, positional encoding, the transformer encoder, and a classification head. It handles variable length sequences with padding masks and uses global average pooling to aggregate sequence representations before classification. This architecture represents a complete, production-ready transformer model for text classification tasks. Excellent! Our complete transformer classifier is working perfectly. It takes sequences of length 25 with batch size 8 and produces 10 class logits for classification. The model has about 6.7 million parameters, making it efficient enough for many practical applications while still being powerful enough to learn complex patterns. This architecture could be used for sentiment analysis, topic classification, or any other text classification task.